Hi, welcome to the Algebra 1 tutor. In this class, we're going to embark on a journey that's going to take you from your knowledge of basic math, which for this course, more or less, we're going to assume that you know how to add, you know how to subtract, you know how to multiply and divide. You've worked with fractions in the past, but we're going to review it in this class. You have some idea what a percent is, all the things that have to do with basic math that have no variables or anything like that. We're going to take you from your basic knowledge here at the beginning of this course and pull you up through the end of Algebra 1 there. So, we're going to expose you to variables and equations and inequalities and all of these things that for a lot of you guys out there, I know terrify you. Okay, that's just the way it is sometimes. The title of algebra has this kind of cast to it that kind of makes you worry about it a little bit. Just the name of it sounds a little bit difficult. But let me tell you, if you take it baby steps, one step at a time, and take every little topic and break it down into little tiny understandable chunks, then by the end of the section you'll find that you do understand it, and more importantly, once you begin to understand it, you'll get some confidence. And that is really the number one thing that holds people back in math. You open up a textbook, you see a bunch of equations, a bunch of letters and exponents and things that don't seem to make any sense because they're nothing to do with what you've learned in your basic math. And so what we're going to do in this class is erase all of that and make it understandable so that you have confidence and so that you'll feel like you can do it, and you can do it. All right, so what we're going to do in this class is start at the beginning. I'm not going to assume you know what an equation is. I'm not going to assume that you know what a variable is. I'm not going to assume you know anything other than what we just talked about. And we're going to go from there. Now here in the beginning of the class, we're going to review some concepts that you typically might see in a pre-algebra course or some other reference that will give you a little primer in pre-algebra sort of in the beginning here. We're going to review some of those topics just to make sure that we don't leave anybody behind, and then we're going to seamlessly move on into what most people would consider Algebra 1. All right, now before we can get into algebra and all the things that you think about, equations and all that stuff, we need to start somewhere. And so what we're going to do in this section, which is called Real Numbers and Their Graphs, what we're going to do is talk about a few definitions. Just like any subject to study, you need to study some definitions and understand them. Once you do that, the terminology becomes easy, and then you can just move on from there. So not too much in the way of real math in this section. There'll be some, but not too much. We're going to mainly learn some terminology. Most importantly, you probably will be tested on this stuff in your whatever class you're taking. So I want to make sure you understand. The first thing we're going to talk about is different types of numbers. We all have an idea of what a number is, obviously, from when you're growing up. But in math, they assign labels to certain types of numbers, and it's just something we do to categorize them. So let's go ahead and go through those. The first type of number that you have experience with all your life is called the natural number. So let me go ahead and write that on the board, and it's written just the way it sounds, natural number. Right? Now, with a name like natural numbers, you might think they have something to do with nature, they might have something to do with, everyday life, and they do. And so basically these things are essentially what you would, if you had to just kind of boil it down to one little sound bite, the natural numbers are essentially the positive numbers. Right? Now in math, they don't like to give definitions like that. They like to have, definitions that have some meaning passed throughout history and things like that. So we call them natural numbers. So the set of natural numbers would be the numbers that you use all your life and that you used to count your jelly beans when you were 3 years old. So they would be things like, 1, 2, 3, 4, 5, ... The little dots mean the numbers keep going and going and going and going. Of course, I can't keep writing them. The little curly braces, don't worry about that. That's just, you'll see it in your book. That just means that it's describing the set. So the way you would write this or read this is the set of numbers inside of these little curly braces describes what we call the natural numbers. Now, the reason they're called natural really is because they're the everyday numbers that we work with. They're the numbers that we use to count cotton balls and the numbers that we use to count our money and things like that. The everyday numbers that you have on your fingers. No crazy negative numbers, no imaginary numbers, nothing like that. Just the regular old natural numbers, and that's why they're called that. So congratulations. You successfully understood your first concept here in our journey of algebra. Now the next little guy that we're going to learn about is the whole number. And you'll see that there's a little bit of overlap really in a lot of these definitions. So the whole numbers typically are going to look like this. There'll be the set of numbers that will look very similar to what we just wrote down. Dot, dot, dot. So again, they go off on, to infinity, up higher and higher and higher. The only real difference between the natural number and the whole number, the set of those numbers, is that the whole numbers include 0. Now, why is it important to have a definition for whole numbers, and why is it important to have a definition for natural numbers? I'm going to be honest with you. My background is engineering and also in physics, but I'm mostly interested in solving problems myself, so I'm not a mathematician. My concern isn't really the theory behind why this is the case, but those of you that are going off to study mathematics as an actual career, there's a lot of theory behind the theory of numbers. But for everybody else that's just studying algebra, and maybe they'll go into science field, maybe they won't, these are just labels. That's really all they are. And so, a long time ago they decided to slap a label on the numbers that are positive, and when you include 0, and they called them whole numbers. And then they have another set of numbers. When you don't include 0, those are called the natural numbers. It's just something you're going to have to memorize. Now, these two guys might seem trivial, and they are, but the next guy is one that you will see a lot all throughout algebra, and we'll probably use the word over and over again: integer. Integers, right? So you probably even heard that number before taking the algebra class you're in now, and if you haven't, then you're definitely going to hear it over and over again. Integers are basically positive and negative numbers. That's the way to really write that down. So if you were going to write down the numbers, you would have something like -4, -3, -2, -1, 0, don't forget 0, 1, 2, 3, dot, 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 right? It's a little curly brace right there. So basically what you have is, starting from 0, it includes 0, the positive numbers that go on to positive infinity that way, and the negative numbers going to negative infinity this way. And the dot, dot, dots are the same thing. It's telling you that it's going off to negative infinity, and this guy's going off to positive infinity. Integers are used so much in algebra, the term is used so much in algebra because we're using negative and positive numbers all the time in algebra. Now I know that a lot of you out there, probably most of you out there, don't really know what a negative number really is. And that's okay, because we're going to explore it in this course. So negative number, when you first hear about it, you're not really sure, is this a real thing? Is this something I have experience with? When have I ever seen a negative number? I don't know what that is. That was my reaction when I first heard of that term. A negative number is something you have experience with, you just don't maybe realize it. It's a convention. Basically, in nature, when you have phenomena, you're always going to have to assign 0 somewhere. And a good example of that would be temperature. So 0 degrees Celsius, right? That is the temperature that water freezes. So we know that if we take a cup of water and we cool it down to 0 degrees Celsius, at that moment that we get to 0, a number that we've, by the way, kind of randomly assigned to the freezing point of water, we just call it 0. There's no reason it's 0. We just call it 0 because it's convenient. That's when water freezes. We call it 0. And we know that all of the temperatures greater than 0 are going to be positive. So as we take that block of ice at 0 and we warm it up, we're going to raise the temperature in a positive direction. Eventually you get up to room temperature, if you keep raising the temperature. But if you take that block of ice and put it in a freezer or in a, Antarctica or something, then the temperature is going to go lower than 0. Negative temperature, below 0 is what we call it. So you see, we've assigned the number 0 to something, and on the positive side we have numbers, and then we have to have negative numbers to cover whatever's on the other side. Another example would be sea level. When you're flying an airplane, the altitude of an airplane is above sea level. When they say we're cruising at 30,000 feet, or 6 miles, or whatever it is, that's above sea level, which is the average water level really at sea level. Now there are some cities in the coastal areas that, because near the coast, if you have any kind of hills or valleys in the coast, you can actually dip down below sea level for some cities. And so their altitude wouldn't be above sea level, it would be below sea level if they had a little valley that went kind of below the average value of the sea level. So they would have a negative negative altitude really. So is that a crazy idea? Is that something that isn't real? Absolutely not. It's completely real. It's just that we're measuring it relative to 0. I'll give you one final thing, and the reason I'm harping on it so much is because negative numbers are just, they're used everywhere. You're not going to watch another section of this course or turn a page in your book without looking at a negative number. So I'm going to spend a little time on it. The third thing that I want you to think about as an example of negative number is the concept of borrowing something. So if I have 2 markers in my hand, then we say, well, I have 2 markers, positive 2. That's over here, right? In my hand, I have positive 2 markers. Now, if I give 1 marker away, I now have 1 marker. Now, if I give this marker away, I now have 0 markers. So now I'm here. So what happens if I start, borrowing markers? Then I don't have anything else. Maybe I want some markers back. So I borrow some markers from my friend. I do have a marker in my hand, but it's not really mine. I don't really have my own anymore. I've borrowed it from somebody else. So you could say that I actually have -1 markers at that point. If I borrow money from the bank, you can sort of say that I sort of have negative money. Yeah, I got money from them, but it's not my money. I actually owe them money. I'm going to have to pay that back. So I'm down in the hole down here. I'm owing them money. And that's what a negative number is. So those are some ways in which to think about negative numbers. They're just numbers below 0. That's really all you have to know. I just wanted to give you a few examples. Integers are the negative numbers, the positive numbers, with no decimals obviously, and 0. So no decimals here, just the whole numbers, positive, negative, and 0. All right. Now, the next thing I want to talk about is very important. It's called the rational number. Rational number. Now let me ask you a question. What do you think of when you see the word rational? When someone is being rational, what are they? That means that they're cool-headed, well thought out, they're cool, calm, and collected. They're rational. You can talk to them. So that's what these numbers really are. It's kind of a descriptive word. These numbers, the rational numbers, are the numbers that we can write as fractions, and which actually is most numbers out there. So we're going to say that the rational numbers are the ones that we can write as a fraction. So let me give you an example. Let's say, the number 1.5. Is this number rational or is it not rational? Well, the question you have to ask is, can it be written as a fraction? Because all rational numbers can be written as a fraction. So can it be written as a fraction? If you think about it hard enough, you will realize that if you use the fraction 3/2, if you put this in your calculator, 3 divided by 2, 3/2, you're going to get 1.5. So that is a rational number. That is a rational number. The number 2 is also a rational number because you can write it as a fraction, 2 over 1. So you see all of these whole numbers that we've been talking about, all of these integers, -5 is also a rational number because we can write it as -5 divided by 1. So any whole number, integer, anything like that, it's automatically going to be rational. And any fraction, so let's say we have the fraction -45 divided by 9. That is also rational. Why? Because it's already written as a fraction. So either the number that you write can be written as a fraction, or, of course, if the number's already a fraction, it's a rational number as well. So rational is cool, calm, and collected in the term of mathematics because it can be written as a fraction. So those are nice, well-behaved numbers if we're able to do that. That's why they call them rational. Another example, the final one, 0.25. Is that number rational? Well, we can write that as 1/4. We can write it as 1/4, and so that guy's rational. So you might say, well, if a number is rational and you can write it as a fraction, then what would you call a number that you couldn't write as a fraction? We'll give an example in a second. What kind of numbers can you not write as fractions, and what would you call them? Well, the answer is you would call them an irrational number, which is kind of a cool name actually, because the word irrational means, or you think about someone that's a little bit crazy. They're not really well thought out. They're not really stable. They're doing their own thing, kind of thing. That's what irrational means. But in the terms of numbers, it's not well behaved like these numbers, and so the irrational numbers are the ones who cannot be written as a fraction. So let's write that down. We have irrational numbers. Okay, irrational numbers. So the definition is you cannot write these numbers as a fraction. Now, the most famous example of a number that you know is irrational, that you may not realize, is pi, the number pi. As you know, that's a really special number. You use it, all throughout math. You'll use it in algebra, you use it in geometry, and trigonometry, and calculus, and on and on and on. You'll use the number pi. And we typically write the number pi as 3.14. That's typically the number that we use when we calculate, the area of a circle or the circumference of a circle or something. But actually, pi is not 3.14. Pi is 3.14159 ... So if you go into a computer or even into a hand calculator and you put, usually in the calculators nowadays, there's a pi button. You just press that button and look at what it spits out on the screen. And it's going to put 3.14159, and it's going to have a bunch of digits after that. And if you go into a computer or a website that would calculate pi for you, then you can go for weeks and look at the decimals that follow pi. You can look to the millionth decimal place after pi, and you'll never find a repeating pattern in this decimal. You'll never find it. And that's why we call it irrational, because you cannot write this number as a fraction. There is no fraction that you can write down that will equal pi exactly. Now, some of you guys might have been taught incorrectly that the fraction 22/7 is equal to pi, but actually that's not true. If you put 22/7 into your calculator, you'll get a number. It'll be 3.1 something, but it's not going to be 3.141592654, on. It's not going to be the exact right number. It's an approximation. So you cannot write pi as a fraction. You just can't. In fact, there are people that do research into this stuff, and they calculate pi to billions of decimal places, trying to find a pattern. It's really amazing that there is no pattern in this number. And anytime you have a decimal with numbers after it that have no pattern to it, you can't write it as a fraction. It's just not possible. So that's irrational. All right, another example of an irrational number would be the square root of 2. If you put the square root of 2 in your calculator, you're going to get something like 1.41 ... blah, blah, blah. You're going to have a bunch of numbers that go on and on and on, but there's not going to be any pattern in this decimal here, so you're not going to be able to find any fraction at all that's going to exactly equal square root of 2. So these are both irrational numbers. So you can sort of see that the irrational numbers are the ones that are sort of special in a way, that you're not able to write them as a fraction. Most of the numbers that you've dealt with in your everyday life, certainly in money and things like that, calendar, time, anything that you would use on a daily basis, they're almost all going to be rational. And that's why we're calling that. They're rational numbers, because they're well behaved. Now, the next thing we want to talk about is in the title of this class. We're going to call this a real number. Real number. Let me make this a little bit better. Real number. What is a real number? Books are going to give you different definitions. My job is not to be a textbook. My job is to break down your textbook so that you understand what it's saying. So go read your definition of a real number in your textbook. I'm going to tell you that a real number is, I'm going to put little quotations here, almost everything. In terms of numbers. It includes the integers. It includes negative numbers, positive numbers, rational numbers, irrational numbers, basically everything. The only thing that doesn't include, it does not include any type of imaginary number or complex number. Imaginary or complex. Now, we're not going to study imaginary or complex numbers too much in this course because it's not that necessary, but I'm just trying to tell you that there are these numbers out there called imaginary numbers. They do exist. You will learn them as you get into Algebra 2 and then in some courses after that, and you use them all the time when you get past that into calculus and other classes. But so there, in the big picture of the world, there's the real numbers and then there's the imaginary numbers. And so everything that you've ever learned up till now, including everything on the board, all the whole numbers, the natural numbers, all these things that we're talking about, those are all real because they're not imaginary. So it's real or imaginary, one or the other. And so a real number is, that's why I say it's almost everything. The only thing it doesn't include is an imaginary number or a complex number, which is really sort of like an imaginary number too. So I don't want to get into the definitions of what these are because it'll just bog us down. But that's sort of what we're after here. Now, some examples. I don't really need to give too many because, like I told you, it includes almost everything, but the number -3. It's an integer, negative number. That's a real number. There's no imaginary, there's no I here, so it's real. 25/2. That's a fraction. That's fine. It's a real number. There's no I here. There's no I indicating that it's imaginary. What about -17/9? That's a fraction. It happens to be negative. That's okay. It's a real number because there's no I here. There's no imaginary number. The decimal 0.69. That's also a real number. Again, there's no I indicating that it's imaginary, because when you start to study imaginary numbers that you'll do in future courses, you'll find that they always have a little I at the end if they're imaginary. So that's why I say they almost include everything. It's just that they don't include those imaginary numbers. Okay. Now, what I want to do now is talk about something really, really important, kind of interesting, and that is called the concept of a prime number. And a lot of you may have heard about prime numbers, even if you haven't really used them too much before, but a prime number is a special number, and the definition for a prime number is basically a number greater than the number 1, right? A whole number greater than the number 1 that can only be divisible by itself in 1. Can only be divisible by itself in 1. That's the definition you're going to find in your book. It's not terribly, understandable at first glance until you really start looking at it. So let's do that now. Let me write down the definition first. So it's a whole number greater than the number 1. So not number 1, but 2, 3, 4, so on. That can only be divisible. And when I say divisible, I mean evenly divided by itself, which is the number you're talking about, and the number 1. So we'll give a couple of examples. Obviously, that's what we want to do. We want to learn by doing. So the number 3. The number 3 is a prime number. And the reason is because you can divide 3 by itself and you'll get the number 1. Right? It divides evenly, right? You can also take the number 3 and divide it by 1, and then you're going to get 3. So that divides evenly also, right? So it's a whole number that can only be divisible by itself and 1. So here you're dividing by itself, here you're dividing by the number 1, and you get a nice even number both times. But if you try to divide this number by anything else, you're not going to have a nice division. 3 divided by 2. 3 divided by 5, 3 divided by 10. You're not going to find another number that's going to divide evenly into it. So 3 is prime, right? 3 is prime. Let me give you another example. 7, right? Number 7. You can take the number 7 and you can divide it by itself and get a nice even number, nice whole number, I should say. You can also take the number 7 and you can divide it by 1, which is what the definition says, and you'll get a nice number of 7. But if you take the number 7 and divide it by 20, or by 4, or by 5, or by 3, or by anything else other than itself and 1, you're not going to get a nice even division. And so because of that, 7 is prime, just like 3 is prime. Just like 3 is prime. So let's look at an example of a number that really isn't prime, and I think you'll understand the difference. So let's look at the number 6. The number 6. Is 6 prime? That's the question. So let's see. 6 can be divided by 6, right? That goes a nice even time of 1. 6 can be divided by 1, and that goes a nice even number of times. You get the number 6. But you can also divide the number of 6 by 3, let's say, and you get a nice even number of 2. So you're able to divide this number by something other than itself and 1. And because you're able to do this, 6 is not prime. 6 is not prime. So most numbers really aren't prime. And it just depends on if you're able to divide it by anything other than itself and 1. So the list of prime numbers, if you're just going to write it down in a list, the number 2 is prime. The number 3 is prime. The number 5 is prime. The number 7 is prime. The number 11 is prime. And there's more numbers as you go, like the number 13 is also prime. But if you notice, the number 4 is not listed here. The number 4 is not prime because you can divide 4 by 2. The number 8 is not prime because you can divide 8 by 4, you can divide 8 by 2 also. The number 10 is not prime, it's not in that list because you can divide it by 5, you can divide it by 2, and so on. So prime numbers also go on to infinity. They keep going bigger and bigger and bigger. It's just that you have to do a little bit of thinking to figure out if it's prime or not. That's basically the definition of a prime number. It's a useful thing. The mathematicians, they study these things. They try to learn about them, understand number theory. For me, it's just another label. Is a number prime or isn't it prime? Okay. Now, the next thing I want to talk about is even and odd numbers. And a lot of you may already know what even and odd numbers are, but if you don't, it's a super, super easy concept to understand. All right, if you're looking at even numbers, basically these are the numbers that can be divisible by 2. So you're counting by 2. So it would be numbers like 2, 4, 6, 8, 10. You see, you're counting by 2s, ... 12, 14, 16, on and on and on. Now, it doesn't matter if it's negative or positive, so negative 2 is also even, negative 4 is also negative, negative 6, it's also even, ... negative 8, negative 10. So anything that can be divisible by 2 is an even number, no matter if it's positive or negative. It's a very, very simple concept, so counting by 2s. Now, an odd number is everything else that's left over. So things like 1, 3, 5, 7, 9, ... Also the negative numbers that go along with this, like, negative 1, negative 3, negative 5, ... like that. So it's everything left over if it's not an even number. Now, one thing I want to show you real quick, look really quickly. If you look at these, okay, this is a prime number. 3 is a prime number because you have it listed here. 5 is a prime number. You have it listed here. 7 is a prime number. You have it listed here. 9 happens to be odd, but it's not a prime number, and that's because 9 can be divided by 3. It can be divided by something other than itself and the number 1. So it's not a prime number. So a number, I'm pointing that out only to show you that a number can have multiple labels. This number is odd. This number is odd, but it also happens to be a prime number. Oh wait, but it also happens to be an integer from our definition before. And oh wait, it also happens to be a natural number from our definition before. So these definition of numbers are just multiple labels to define the buckets that you can put this number in, and most numbers are going to have more than one label. Because, by the way, this is also a rational number because it can be written as a fraction. You can write that as 7 over 1. You can write that as 9 over 1. So there's more than one thing to think about when you're looking at these things. And so in your test, a lot of times what will happen is they'll give you a number. And they'll say, tell me if it's rational, tell me if it's prime. List everything you can about this number, and so you'll have to do that. You'll have to do that. All right, now the next thing I want to talk about, we'll switch gears here. The next thing I want to talk about, sort of switching gears, is the symbols that you're going to find. Symbols. There are a lot of symbols in algebra that you're going to learn. Parentheses we're going to get into, and all these things that look foreign, and that's why it scares a lot of people. But we'll break it down one step at a time. So let's go with the super basics, the thing that you already understand. Let's talk about the equal sign. I like to talk about things that everybody understands. All right, so it's something you have to understand. So the equal sign, there you go. It's a symbol that you've used all your life. How would you use an equal sign? I mean, you know the answer to this, but you could say something silly like 2 is equal to 2. That's your first equation written right there on the board. It's a silly equation. It doesn't really mean anything. All it says is if I have 2 jelly beans over here, that's exactly equivalent to, this other bucket with 2 jelly beans. So if I have 2 jelly beans here and 2 jelly beans here, those are equivalent number of beans. That's what it's saying. Everything on this side of the equal sign has to be equal to what's on the other side of the equal sign. So that's really simple. Let's talk about something that you may not have seen. You can also say something like 3 is not equal to 2. Now this symbol is an equal sign with a slash through it, and that just simply means that the two sides are not equal. It's exactly what you might expect. The 3 jelly beans over here is not equal to the 2 that I have in my other hand. All right? And then finally, we need to spend a little bit of time talking about greater than and less than. which I know you've seen before, but I'm going to hopefully make it really easy to understand. We can write something down. Let me draw a little line to kind of divide off here. We can write something down like this. The number 2 is less than the number 3. And you know, all right, you all know that the number 2 is less than 3, but we need to use our symbols to write that mathematically, because the math is basically describing what we know to be true. And as you build your skills, you'll be able to solve problems that you can't do in your head. So we have to make sure we understand everything. 2 is less than 3. How do you read this? This little symbol here, you probably see it in your book. It's called the less than symbol. Less than symbol. And then if you flip it around, and we will here in a second, you'll call it the greater than symbol. So let's do that right now. Let's say the number 5 is greater than the number 1, which I know that you all know to be true. And we say that this symbol is the greater than symbol. It's the greater than symbol, which is exactly true. There's nothing wrong with that. But here's the deal. I want you to not worry too much about these guys as far as being separate symbols. You know, a lot of books will say, here's the less than symbol, and here's the greater than symbol. Here's, you know, you need to use them whenever you need to use them. I prefer to teach you that whenever you're comparing two things, just take this arrow and point it always to the smaller number. I'm going to say that 2 more times to make sure you understand it. Always point that arrow to the smaller number. Always point that arrow to the smaller number, Because that's really what the symbol means, really. It's an arrow, and so the smaller side of this arrow, the side that comes to a tiny little point, should always be next to the smaller thing. The bigger part of the part of the arrow that's big and fat, should always be next to the bigger thing. So you see, the arrow is always pointing to the smaller thing here. It's pointing to 2, because that's smaller. And here, the arrow is pointing to 1, which is smaller. So yes, you could say they're separate symbols because they point different ways, but really it's just one symbol. It's an arrow, and the arrow points always to the smaller number. So in this case, we have the arrow pointing to the smaller number as well. And so try not to think of these things as 2 separate symbols that you have to memorize them. Try to think of them as just an arrow that points to the smaller number, and then so when you do that, the bigger part of that arrow is going to point to the bigger number, or be next to the bigger number. And when you read it, you just read it just like you would in a sentence. 5 is greater than 1, 2 is less than 3, and that's how it comes about. Now, you can also do some interesting things with these things that you're going to need to understand. And so it's sort of building upon greater than, less than, so we're going to do that now. What I'm going to do, I talked in the beginning of the course that the word variable scares a lot of people. All right. So what I need to do now is sort of introduce that, just to sort of teach you a little bit more about how to graph these inequalities here on a number line, and introduce the number line, which is half the reason we're teaching this section here. So think of if you don't know the answer to a problem, you know, when you're younger and you're adding up jelly beans, you know, you're just basically counting them and you arrive at the answer. When you get up into algebra and beyond, when you don't know the answer to something, you assign it a letter. And that letter is just something, you don't know the answer to it. It's called a variable. It's just a letter that just represents whatever the answer happens to be. And that's a variable. So when you solve your equations later on in the class, you're just going to solve for the answer to that problem. It's going to be the answer to that variable. Now here I'm going to introduce the variable x. You're going to see the letter x used a lot because it just happens that algebra uses the letter x to represent the variable most of the time. It's a letter of the alphabet. You've seen the letter x all your life. Don't be worried about it. It's just an unknown value of something. So if I had something like x is greater than or equal to 6, I would write it like that. Now this symbol looks very, very similar to this symbol, but there's a difference. This one has a line underneath it. This one has a line underneath it. And that line is basically telling you that whatever x is, it's got to be greater than 6, but it can also be equal to 6. That's what the line under there means. If there's no line, then it's just, if you're just looking at it like that, it's just x is greater than 6. So 7, 8, 9, 10, 11, 12, and so on. That's what x could be. But if you make it greater than or equal to 6, then x can be everything including 6. So in this case, x is greater than or equal to 6 is how you read it, and the answer would be that x is equal to 6, 7, 8, 9, 10, dot, 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 on and on and on, if we're talking about integers here. So x is greater than or equal to 6. So it's basically including 6 because of the equal sign. That's why we list it. And then every number bigger than that because we're talking about numbers bigger than 6. Now, just to give you another little example, if you have y is less than or equal to 3, right? That's the way you read it. Less than or equal to. That's the way you write that. Then y is going to be equal to 3, 2, 1, 0, -1, -2, dot, dot, dot. Because basically it's equal to 3. Y can be equal to 3, but it can also be equal to 2, to 1, to 0, -1. You keep going less and less and less. And so when you think about it, if you get less than 0, you're going to be going into the negative, into the realm of the negative numbers, which is what we talked about. So that is the symbols I wanted to show you. We have the simple equal sign, we have when two things are not equal, and we have greater than and less than, which are exactly the same thing. You just point the arrow to the smaller number. And then we have greater than, equal to, less than or equal to. And in these cases, you're basically trying to express a whole range of numbers, either bigger or smaller than the number you have. And if there's a bar under it, it includes that number. And if there's no bar listed here, well, then you wouldn't include that number. That's really all that that means. So let's go ahead and erase the board and start actually graphing numbers on the number line. Okay, now we've done a lot in this section. We've talked about numbers. We've talked about categories of numbers, labels for these numbers. We've talked about symbols, greater than, less than, equal to. And we've kind of danced around the issue of a number line, but we've never actually done that and drawn that. So that's what we're going to do now. Imagine all the numbers that you've ever known stretched out on a line. And so, you know, numbers can go on forever, so the number line goes on forever. And it goes off into the positive direction, because the positive numbers go on to infinity. And it also goes on to the negative direction, because the negative numbers also go to negative infinity. And so this line really is double arrow line, and it goes in both directions. So what we're going to talk about now is the number line. And, you know, you need to get comfortable with it, because I'm going to tell you later on, when we're going to start adding and subtracting negative and positive numbers, the number line is going to help you do that and help you visualize it. The number line is a very simple concept, just like we talked about. It's a line. The little arrow means it goes on forever, and the other little arrow means it goes on forever that way. Now, in the middle of the line, just like we said, you always have to have a reference point. You always have 0 in the middle. And so over on going this direction, you have your positive numbers, 1, 2, 3, you know, and then you have 4, 5, 6, 7, 8, 9, 10, and go on forever. I'm only going to draw these. And then I'm going this direction, you have -1, -2, -3, and then keep going, you would have -4, -5, and they would go on to negative infinity there. Now, if I were going to graph a number on this number line, it would be a simple matter of putting a dot wherever I want the dot to go. So if I were going to plot the point -1 on this number line, I would put my pencil right on top of this mark for -1 and put a dot there. This would be the graph of the number -1 on this number line, and you immediately see how it relates to all the other numbers. So if I wanted to put, you know, plot the number -3, I would put a big fat dot on -3. Now notice that even though the numbers on the number line are you know, they're whole numbers, you can plot points in between those numbers. So if I were going to plot the point 2.5 or 2.5, then I would go right between 2 and 3, and I'd put a dot right there, and I would say this one is 2.5. And you know, this number line, you don't want to put too many numbers here, so you just put the whole numbers, and then anything in between that you plot, you just, you know, put it as best you can. So that is the concept of a number line. It's not a complicated concept. It's a line with numbers, and you use it to represent and plot the points on there. It's going to help you visualize negative numbers and positive numbers, and that's going to be really useful. Now let's say that I wanted to do a little bit more with that. Let me draw another number line. Right, so I'm going to go do the same thing before. 0, 1, 2, 3, -1, -2, -3. Now, what I want to do here, what if I wanted to graph the inequality x is greater than -2? And when I say inequality, by the way, when something is equal, you know, that would be something that was, you have an equal sign in there. When something is unequal, you call it an inequality. These greater than or less than symbols, they're just called inequality. So if you hear me say the word inequality, it just means it has one of these symbols there. That's it. So what this number means, or what this thing means, is that x, which is some number that you're just trying to represent here on the graph, has got to be greater than -2. Got to be greater than -2. So what we're going to do is we're going to put a circle right on top of -2, because that's a number here, and x is every number bigger than that. So we're going to actually shade the number line, and you do this on your paper. You would literally get your pencil out and you would literally shade it like this. So this graph is telling you that x is greater than -2. You start at -2, and every number bigger than that is what's represented. Now notice, very, very important, this circle here around -2, it's an open circle. When you have an open circle, when you're plotting these guys, it means that you're representing every point bigger, but you're not including -2 itself. In other words, -2 is not represented here in this little inequality because we said x is greater than -2. We didn't say it was greater than or equal to. We didn't say it was equal to -2. We just said it had to be greater than. So if something's greater than 1, it can't be 1. It has to be, 2, 3, 4, 5, whatever. If something's greater than -2, you cannot include -2 in the answer because we said it's greater than -2. So we put an open circle to remind us that -2 is not really part of this answer, but everything bigger is. All right? Now, if we change the problem, if we change this so that we said it was x greater than or equal to -2, that would be something different, and in order to represent that, the way we would have graphed it, and instead of drawing it again, I'm just going to go right back up here. Everything is exactly the same, except we have to make this a solid circle. Because this solid circle is telling us that, yes, -2 is included in that, and it's -2, and it's everything bigger than that. So that's very, very important. It's a great place to make a mistake on a test. If you ever see any open circles, then you know that number and that point is not included in the inequality. And if you see those closed circles, then you know that it is. So it's very important for you to know. All right, let's do a couple of additional examples. Let's say, let me draw another number line. So we have 0, 1, 2, 3, -1, -2, -3. Now let's say I wanted to represent x is less than or equal to -1. X is less than or equal to -1. Well, the first thing you have to say is, well, -1 is what I'm looking at, so I have to put a circle here, and it has to be a closed circle. And the reason it has to be closed is because it's less than or equal to -1. So -1 is included in the answer, and since we're talking about numbers less, we're going to shade this direction. So every number way down here below -1, all the way to -infinity, is included in this, in what this is trying to represent, including the number -1, and that's why we have a solid circle there to remind us of that. So don't get too confused, and definitely don't make any mistakes with the open versus the closed. You have to pay attention if it's less than or equal to, or if it's not equal to as well, and that's why that's important. Now let's go on and do something similar. But in this case, we're going to do a little bit different. I'm going to draw something on the number line. 0, 1, 2, 3, -1, -2, -3. And what I'm going to do is I'm going to first draw it, and then we're going to write down the inequality that it represents. So let's put an open circle here, and let's shade this direction. Okay. And let's go ahead and put an open circle here, and let's shade this direction. Okay, so we have two open circles, and they're both going opposite directions. Now the question is, how do you write that down? What would be the inequalities that you would use to represent that? Well, it looks really confusing, but you need to break it down into two parts. You have this part, and you also have this part, so let's write that down. This part is going to be x is less than -3, and the reason is because of course it's less than -3 because we've shaded that. It's an open circle, which means we're not going to have any equal sign here because -3 is not included in the graph. We also have a second part, and this is going to be x is greater than 1. Again, it's an open circle, so you don't have an equal sign here, and it's greater than the 1, so we're going to have it like that. So this really is the answer. It's two separate little inequalities, and that's what's representing the graph, but you can combine them. And a lot of times they'll do this on your test, and it confuses people for no good reason. And so let me show you. The way you combine these things is write your x in the middle. So what we do is we write x in the middle, and we say x is greater than 1, which is exactly what we have here. So far we haven't done anything other than rewrite down what we have. But we also say that x is less than negative 3. And so here we've combined the two things, but in order to read it properly and to not get too confused by it, because it does look confusing, I'll admit to you, you have to start in the middle. A lot of people try to start reading it over here and it gets really confusing. Read in the middle. X, so forget about this. X is greater than 1. Okay, great. X is greater than 1. It's not including 1, so there's no underline here. It's just greater than 1. So that's what happens if you cover this part. Now if you cover this part of it up, then if you read it properly starting at x, x is less than negative 3. X is less than negative 3 because the arrow is pointing to the smaller thing. So x is the smaller thing. X is less than negative 3, reading it from the inside out. And x is less than negative 3. And that's why we have it written that way. So if you try to start reading it here, you can do it. I'm not telling you that you can't do it. But for me, it's always easier if you start in the middle. X is greater than 1. Okay, that's what I have. X is less than negative 3. Okay, that's true. This is what you'll see a lot of times on your test. Sometimes they'll give you something like this, and they'll say graph it. The first thing people do is freak out a little bit and panic. Just cover up half of it and graph that, and cover up the other half and graph that, and you'll be in really good shape. Let's do one more similar to that. It's an important skill to have. It's an important skill to have. So we'll have 0, 1, 2, 3. Negative 1, negative 2, negative 3. And let's say the graph that we're after is going to be, let's change colors a little bit. Let's say negative 2 we're going to have a dot on, and positive 3 we're going to have a dot on, and we're going to shade everything in between these two dots. Question is, what inequality or inequalities could be written to represent that? And so again, you have to take it one step at a time and put them together without trying to, go straight to the final answer. You need to work in steps. So what you need to first look at here is say, okay, x is greater than or equal to negative 2. Because here's negative 2, here's a solid dot, so it's greater than or equal to negative 2 because the shading goes on to the bigger numbers. So it is greater than or equal to negative 2. However, it doesn't go on forever and ever, so we also know that x is less than or equal to positive 3. X is less than or equal to positive 3. It has the little equal sign there as well because you have another solid dot. Okay, so this by itself would be solid dot going on and on to infinity. This by itself would be solid dot going on and on to negative infinity. But together, when you put them together, it just represents the range of numbers here. Because when you put them together, the way you would write that, you put x in the middle and do exactly what I said. You would start with one of them, greater than or equal to negative 2, just rewriting this, and also less than or equal to 3. And if you look at it, this part is just totally rewritten over here, and then all the other stuff on this side, right here, is just this, but flipped around a little bit. So the arrow's pointing to x, here the arrow's pointing to x, big part is pointing to 3, big part's pointing to 3. So this is really exactly the same thing as this, it's just written with x in the center. So the way you read it is you start in the middle and you say x is greater than negative 2, check, and x is less than or equal to 3. So x is greater than or equal to negative 2, and x is less than or equal to 3. And so you put those two things together, it's representing the region of points between those two numbers and including those two numbers because of the solid dots there, because that's what that represents. So this is, there's probably a fancy word for it, but basically it's a double inequality. It's when you're describing a range, or you're describing two parts of the number line, and using both of these together, you can rewrite it. So don't be afraid to look at this and pick it apart to graph it and go in reverse, or if you're just looking at a graph, write them down individually and then combine them into something like this. All right. Now, the next thing we're going to talk about, which is actually going to be the last thing in the section, is also very important, and that's going to be the topic of absolute value. Absolute value is one of those things that's pretty easy, but has a big word, has a big name, so a lot of people get worried about it. Basically, the absolute value of a number is just telling you how far away that number is from 0. How many units of distance is that number away from 0? So the easiest way to do it is just to draw a number line and take a few examples. So here's a number line. Here's 0, 1, 2, 3. Of course, it goes on forever. -1, -2, -3. It goes on forever that direction. So if I were going to ask you, what is the absolute value of the number 3? Just regular old 3. All you have to do is take the number on the inside and write it down. That's the answer. The absolute value of that is 3 because the number of distance units the number 3 is away from 0 is simply 1, 2, 3. 3 distance units. All right, so the absolute value of 5 is 5 for the same reason, because if you have 4 out here and 5 out here, the distance that the number 5 is away from 0 is just simply 5. So you say, well, this is silly. Why are we even learning this? Well, the absolute value of -6 is equal to what? It's equal to 6. The absolute value of -2 is equal to what? It's equal to 2. And the reason is because if you look at -2 here, which is right here, how many distance units is that away from 0? It's 1 distance unit, 2 distance units away from 0. So yeah, the negative numbers do go on the other side of 0, true, but the absolute value, the value that you have independent of its sign, the distance that that number is away from 0 is always going to be a positive number, even if the number itself is negative. And so you're just counting units. That's all you're doing. Practically speaking, all you have to do, if you have an absolute value of 10,347 negative, is just going to be 10,347. Whatever you have in the inside is what you write down as the absolute value. No matter if it's a positive number, the absolute value is positive. If it's a negative number, the absolute value is positive. So that concludes our section in real numbers and their graphs. You see, we've covered a tremendous amount of material. We've talked about numbers. We've talked about integers and all these categories of numbers, real numbers, rational numbers. All these things are just kind of can seem to be a little bit of mumbo jumbo, but you have to learn them. Number one, because you're going to be tested on them. But number two, it's sort of the language of math. If somebody says, hey, here's an integer in this equation, you need to know what the word integer means, because if you don't, you're just going to get scared by it. And the number one thing you need to realize is that if you understand something, you build your confidence up, and when you do that, you know that you can conquer everything else that follows. I guarantee you, every one of you guys, when you were all babies, when I was a baby too, we learned how to speak in the English language. We didn't have a textbook. We didn't have a teacher. We just listened to people. And somehow out of all of that came the ability to use words, and then sentences, and then paragraphs, and then we can write things down and make long, stories if we want to. It's an incredible thing that a child can do to learn how to speak without any books or anything. They're just listening by examples. They're listening to what people are saying, and they're putting it together, and their brain's putting it together. That is how I plan to teach this entire course, and all of my courses, is by examples. So rather than put a bunch of definitions on the board, really lengthy ones, like you'd see in a book, we're going to do it by working problems. We're going to do it by examples, so that if you see enough of these things, you'll realize, yeah, I do kind of understand how to add negative numbers together. I really do understand how to multiply fractions. I know how to solve equations because I've seen it done so many times. Building one skill at a time. I'm Jason. I hope you got something out of this lesson. Stick with me on this journey. I guarantee you that you'll be comfortable in algebra, but not only that, you'll be really, really good at it.